as always, very quick reminder, the sum is about statistical analysis method for subjective experiment. So actually, Loy presentation would fit very, very well to the sum. And this is, as we discuss, always there is some crossing. So, well, it always will be like that. So anyway, we've got 4 presentations, and without delay, I would like to go for them. The first 2 are given by Dietmar. So please start.
Yes, thank you very much, Lucian. I tried to share my screen a couple of minutes ago and it did not work. I'm afraid it still does not work. The system says I should allow, or the system needs to be
extra permission. I had this problem on a couple of times. Like, I don't know, it's coming and going. If you want and you can send me, then we can start with shell presentation. And if you can send me the slides, then I can share them. Oh, it works.
Let's see now. Is it working? I tried again.
Yes, perfect.
Oh, I don't. Okay, let's see. I don't see it on my screen. Can you see my
yes, maximum entropy?
Yeah. Okay. So, well, that's strange. All right. So then I'll just start. Okay. So if you stop hearing me or so, or seeing the slides, just let me know, and then we'll see. Okay. So I have 2 talks. The first one is about absolute category ratings. So the usual BTC scale from bad to excellent. And the second talk is about pair comparisons or triplet comparisons. And I must say I'm more a supporter of triplet comparisons, but surely also the 5-level ACR has its justification. It depends on the application. So the first talk is about maximum entropy and quantized metric models for ACR. And this is joint work with Christoph Ruschek, David Hegele, Daniel Weiskopf, and Lucian. It has just appeared as a small paper in the IEEE signal processing letters this year. Okay, so we all know about the 5-level categories scale in ACR from bad to excellent. So this is a discrete scale. And of course, in the background, there is a continuous scale that underlies this scenario. And sometimes some people also use the visual analog scale to try to assess this continuous scale more or less directly with a slider that you can move around from 0 to 100 or from 0 to 1 on some interval to collect these ratings. But this is about the discrete category scales. And what people usually do is to collect the mean opinion score. And this is what's being published together with a data set. For example, we have done the Conic 10K data set that was already mentioned in the previous session with over 10,000 images. They were uniformly sampled with content with respect to feature brightness, colorfulness, and so on. And we collected about 1.2 million ACR ratings using crowdsourcing. On the right here, you can see a snapshot of just 900 of those images sorted in 2D according to content, which was approximated by VQEG 16 deep features. And then there's the VQEG HDTDV data set that we use. So this was produced by groups here in VQEG some years ago, 864 videos in several lab studies, joined together then in this data set. And each one contains about 24 ACR ratings per video. Conic 10K has a lot more ACR ratings per image, more than 100 on average. Okay, so these are the 2 data sets that we use in this study. And what we want to represent these rating distributions. So let's look at the picture here on the right. So here we have the first 8 images in Conic 10K with their names, and these are the 5 categories, and you can see the frequencies of the ratings. So the first one has 25 fairs, 73 goods, and 7 excellents, but no bad and no poor, etc. Okay, and so the MOS is considered the central result of a rating, and then all objective image quality metrics, they aim to predict the MOS. But is this enough? Should we stop there and or not consider a little bit more? So a while ago, no, 13 years ago, there was a paper at QMX by Osfeld et al. Called SOS, the MOS is not enough. Okay, they found this kind of catchy title, and it gave them a lot of references, but mostly because of the content was important, not because of the title, of course, what the title helped. So SOS, the MOS is not enough, is not something that comes to the rescue in an emergency, but SOS just stands for a standard deviation of opinion scores. So they said, okay, besides the MOS, we should also report the standard deviation of the ratings for each image or for each stimulus. So this shows the user diversity or item difficulty, as both are contained in the SOS. Okay, and so they looked at the internet movie databases, and they showed that, yeah, for a given MOS, there are many ratings or many images or movies here with vastly differing quality ratings or variances, let's say, of the standard deviation here. Okay, and then they put forward the SOS hypothesis, saying that the variance, of course, of all, is bounded by a quadratic function, and you can fit a parabola to this experimental data. And then if the amplitude is considered, so it's kind of like the scale of these parabolas here, or, well, these are square roots of parabolas. The larger the scale here is, the more unreliable the data is, the higher the variance per stimulus, and so the less reliable it is. And then they proposed, okay, if you look at the variance again here, so on this scale you have highly precise or accurate lab studies here at the bottom, and more variable studies here for gaming and web applications that have a larger SOS parameter. That means a larger amplitude of these parabolas here. Okay, so that was that, and for our data sets, Conic 10K and VQEG HGTV, these are these plots of variance versus the MOS, and you can see the upper bound here and of the parabola and the lower bound, which looks like this. And all the dots here correspond to the images in Conic 10K or to the videos down here. And it shows a curve, or if you approximate the point cloud with a curve, a parabola, it is lower than the experimental data here on the left they had. So this is for Conic 10K, and it indicates that according to the hypothesis that it is a good data set with not so much variance per stimulus. Okay, so but the next thing is that we would like to maybe model even further. So what is the population-wide rating distribution? Not just the mean and the variance, but more. What can we do more? So the distribution Q1 to Q5 in the full population. So can we somehow estimate that? And the recommendation that Hosfeld and another paper, Seufert, put forward was, okay, we have these empirical sample distributions, P1 to P5. So these are the empirical ratios, the frequencies. And we should just use those and report those besides the MOS and the variance, or in place of MOS and variance, because that's the MOS and the variance can be derived from the probabilities here. And then the fundamental theorem of statistics says that this is okay for large n, but for small n, one probably has some overfitting. So this was one of the rating histograms I showed on the second or third slide. And so we didn't have any ratings of the category poor here. Does this really imply that the probability in the entire population is 0 for giving a quality value of good? Surely not. So there is some room for improvement here. And this is our contribution of this paper here. We wanted to put forward some 2-parameter models for these rating distributions that are statistically reliable and that are better than these empirical sample distributions. And so in the rest of the talk, I will explain what these models are and how we how we attested that they are statistically reliable, and how we found out that they are better than these empirical sample distributions. Okay, so the first type of model is a quantized metric model. So a quantized metric model is as follows. As I said, we have underneath the surface of the ACR a continuous quality distribution on the so-called latent variable, the quality scale, and then there is a threshold that we can say three thresholds between the ACR ratings 1, 2, 3, 4, and 5, and we put these thresholds here right in the middle. And then the area underneath the curve of the distribution of the quality in the population, or in the population of the participants of a study, then would be the probability or the frequency then of the ratings from bad to excellent. So if we if we find out such a model, then we have these model probabilities, and these thresholds here are fixed. And yeah, this is also called an order probit model then in some literature. So for the continuous distributions here, we can use the Gaussian, the normal distribution, but we could also use the logistic one, which is very similar. These are on the real line, or we can also look at distributions on an interval, the unit interval, and examples are the beta distribution or the logistic distributions. And I said we wanted to have two parameter models, and so the two parameters, the canonical ones, are the mean and the standard deviation sigma. Okay, so this is the first type of metric model. And then how do we estimate the parameters? Well, we use the maximum likelihood parameter estimation. So this proceeds as follows. As input, we have the sample distribution here. So we take this from our data sets, Conic 10K and VQEG HDTV. And the output should be this distribution Q1 to Q5, which depends now on our parameters mu and sigma that we need to identify. So QK then would be the probability for the kth ACR bin. So to carry this out, we have to minimize the cross entropy, which is proportional to the negative log likelihood. And so this is the formula down here is the cross entropy. And you can see that it is a log likelihood, the negative log likelihood, the minus sign negative, pk, the probabilities that were observed, and q is then the model, the log likelihood. So we minimize this and find out for which parameter mu and sigma the minimum has occurred, and this is mu hat, sigma hat, our estimate. This is a nonlinear optimization problem. You cannot solve this analytically on a piece of paper. You have to do this numerically. But that's not a problem. Okay, that was the first type of model. The second type of model is something that was really new. The first one was known. This is not invented by us. But this one here is a new one, and it's based on the principle of maximum entropy, which for this case here says if nothing is known about a distribution except that it has a certain mean and a certain variance, then the distribution with the largest entropy should be chosen as the least informative default. Okay, why is this? Yeah, the maximum entropy minimizes the amount of the prior information that is built into this distribution, and many physical systems tend to move towards this maximal entropy configuration over time. So there's evidence in natural sciences and in information theory that says so one should use these distributions if we have some prior information that consists of mean and variance only. So the probability distribution Q with a given mean and variance that maximizes this entropy H of Q, that's called the maximum entropy probability distribution now. For our paper. Of course, in other situations, you have other prior information, and then it's a little bit different. So again, we have to estimate the parameters mu and sigma with maximum entropy. So it's the same input, same output, and we minimize again the cross entropy. But now in the cross entropy here, the model is Qmax, namely the maximal entropy distribution. So That, again, is an optimization here. We have to maximize the entropy overall quality distributions Q with a prescribed mean and standard deviation sigma. Okay, so to solve this optimization problem, one has to do a nested nonlinear optimization. And this makes it numerically very unpleasant to work with, because in each optimization, you have some errors, and then that means that in the outer level optimization, you're working with only an approximate version of the Qmaxes here. And so you have, serious error propagation there. All right, one more thing. So you have to do the optimization. You have to provide some initial guesses for this. And then, of course, the natural initial guess for mu and sigma is the empirical MOS and the empirical SOS, the sigma. And let's call this the oracle. So this will give us a distribution without underlying continuous distribution. And in spite of the problems I just mentioned with the numerical issues, you can program this in. It does give some reasonable results. I did that. Now, however, there is a rescue with these problems, namely the following theorem. Let's call it the oracle theorem, which essentially says that the oracle is exact. It's correct. So let's mu hat and sigma hat be the empirical mean and standard deviation that we just take from our data, from the ACR study in conic 10K or VQEG DTV. So mu hat is the MOS and the sigma star is the standard deviation. And then the theorem says that Qmax of mu hat mu sigma. So if we maximize the entropy for all models that have the prescribed mean mu hat and sigma hat, that is already the optimal empirical probability distribution that we were looking for, that matches the P. So that optimizes the cross entropy. So now we have done away with one of those optimizations, only one is leaving, namely the second one here. We have the oracle, and so we just insert it in here, and then we're done. And so this is much faster and much more precise. Okay, that's that. And then the third type of model is a generalized score distribution, which was developed a while ago by Navala et al. Also, Lucian was involved in it. It's a discrete distribution like our maximum entropy distribution without this continuous distribution lurking underneath. It's a complicated mixture of binomial, beta binomial, and 1 or 2 point distributions. Okay, and one of the properties that was put forward in their papers was that it describes ACR response distributions that were observed in typical experiments. By typical, they have meant that these are experiments that are done in the lab, strictly following the rules of BT500 and other standards. Okay, so that is the first part. So those are our 3 types of models, and now we discuss how to how to analyze that these models will actually give us a statistically valid approximation or estimate of the ground truth, an estimate of the a good model of what we have measured. So the G-test is such a hypothesis test that compares the goodness of fit for our model with that of the empirical model, which is then based on the ratio of the likelihoods. So this is the formula for G. You can look it up on Wikipedia. It's there. And so it is 2 times the number of ratings for one stimulus times the difference of the cross entropy and the entropy of the empirical data. So if you minimize the cross entropy, which is what we're doing, then you also minimize the G-test statistic here. And with this notation here, it's as clear that the G-test is always greater or equal to 0. So 0 is a lower bound that you can try to achieve, but the lower bound for H of P and Q is larger. It's a positive number, and it depends on the P, and it's so less a little more difficult to or more difficult to interpret, let's say. Another property is that G has been shown to be asymptotically chi-squared distributed, and so we can extract p-values from the distribution of the G values. And there are 2 degrees of freedom. So an ACR distribution has 5 values, but they sum up to 1. That takes away 1 degree of freedom, that leaves 4. And 2 degrees of freedom are removed because we prescribe or we estimate mu and sigma, so that leaves 2 degrees of freedom. And then you can read it off from the table or from this graph of the distribution, the chi-square distribution, that if the G-test is larger than 5.99, then the p-value is of just 5%. And if we are less than 5%, if we're less than 0.05 for one distribution in our model, then the model should be rejected at the 95% confidence level. Okay. Another estimate of the model quality is the Akaike information criterion, and it's an estimator of the prediction error and thereby a relative quality of a statistical model for a given set of data. And it is this formula here. L is the likelihood, so it's 2 times the log likelihood, or minus 2 times the log likelihood, plus 2 times the number of parameters. And for us, and the K is a total number of parameters in the data set, so this is tens of thousands. Okay, this is very similar to the G-test, and in our case, all of the models have the same number of parameters, so it boils down to the log likelihood, essentially. So it's equivalent to the G-test in our case, and we include it in here only because it's more popular than the G-test. Okay, now the other type of analysis was, can we show that our model is better than the empirical model that we just take straight from the data? So for this, we have to analyze the prediction error. So, in other words, we generate a model from our data, and then the model should predict unseen new ACR ratings that were not seen by the model or by the training. So for this, we take a sample of n ratings from conic 10K in this case, and we subdivide it randomly into 2 subsets, a training set and a test set. So the training set with m less than n ratings, and all the others are then in the test set. So from the training set, we compute the model Q, and then we can compare it with the empirical model of the test set. Let's say T is the test set distribution of the ratings from 1 to 5, and then we can report the prediction error, and we have used the infinity error between our model from the training set and the values from the probabilities from the training set T. So this is feasible for conic 10K, but not for a VQEG HDTV. We have 10,000 items with more than 100 ratings per item. So there we use, for the training, 11 to 40 ratings out of those 100 per item, and the others are all for testing. For VQEG HDV, we have only 24 ratings per video, and then that's not going to be very conclusive then. So this is the result for conic 10K now for the first part, goodness of fit. And we have these logistic models here, the max entropy, the beta, the logistic, and the GSD. All 6 models are in here. Here's the AIC, and here's the G-test. So smaller is better, and the ranked is according to the G-test. So the smallest is at the top. And so we see here that the logistic model is top, and the GSD here is at the bottom. And here's a column for the p-value. So we set at p equals 0.05, there's a threshold, and we can accept the model if the p-value is larger than 0.05, or rather reject it if it's smaller than 0.05. And then the question is, out of those 10,000, how many would we have to reject? And that's what this last column here says. So for the logistic model, we have to reject 3% of the models. They do not satisfy this statistical p-value test. While for the others here, the value is slightly above or more above 0.05. Okay, so if we have to reject 3%, then that is an indicator that the logistic model here is okay, because statistically we should expect at a confidence of 0.05 that we can reject 5%. And that's by definition of this p-value. And so we only have to reject 3%, so that's better. And so the logistic model is a faithful model for the conic 10K ratings, 10,000 of them that we have. So the logistic model passes globally the p-value test. Okay, and we can also plot this here. So this is the cumulative distribution of the g-test value for the 10,000 stimuli, and the dashed line here is the line that we would expect for the chi-square distribution, and the logistic curve is above this dashed line all over this range, and that leads to the only 3% rejection ratio. How does it look for the VQEG HGTV? So here we have the same table as before. Again, the rating, and this time it's not the logistic or logistic that at the top, but all of these models are good. So see, all of the percentages are below 0.05. So this means all the models here globally pass the p-value test for VQEG HGTV. So they're all statistically valid. So, and this is the curve for it. So they're all above the line for the chi-square distribution. So that's a good result for the models that we have. Now we come to the prediction accuracy. So the question was, is our model a better one when it comes to prediction of unseen ratings that were not in the training set? So in the first column here, we list the size, the sample size of the ratings from 10 to 40. And so the models were based on these 10, 15, 20, etc. sample sizes. And so then we looked at the test set and compared the resulting model with the test set. And this is the L infinity error here. So 0.01 down to 0.05. Of course, the higher the sample sizes, the better we can approximate the distribution in the population, and we get a smaller L infinity error here. Okay, so this is the model of the logistic distribution, and this is then here the model for the empirical model. So we can also, of course, take this these samples here of 10 ratings and take the frequencies in these 10 samples as the predictor of the frequencies in the test set, and then compute the L infinity error. So this is the empirical model for prediction, and here we have our derived model from the maximum likelihood estimation for the prediction. And we see that the L infinity errors for the empirical model are larger than the errors with our model that we have trained. So this indicates that we have an improvement here, but then the question is this really statistically significant, this improvement? How large is the effect? So for that, we calculated the Cohen-D effect size. And so this essentially looks at the distributions of these errors over all 10,000 samples that we have for the 10,000 images, and they look at the sigmas of these distributions and take into comparison the difference in the means versus the sigma of the samples here. And then we get to the Cohen-D here, and these are then interpreted on a scale, and this would mean here that our Cohen effect size is large or very large. So yes, these differences are statistically significant, and we could then say yes, our models predict the unseen ratings better than the empirical model. So this is better than what Hosfeld and Seufert had proposed. How can we quantify it maybe in a little bit different way? We can look at the gain. Let's look at the curve over here on the right. So this shows us the sample size versus the prediction error here. And the blue curve is for the logistic model, which was accepted by our studies as a statistical model. And the empirical prediction error is the dashed line here. So, for example, if we take a sample size of 20, which is well in the range where BTC 500 would propose, then we can see, if we go to the right, how many more samples would we need for the empirical model to reach the same prediction accuracy, the same prediction error that we have for the logistic. And so the difference here, the horizontal one, is about 2 units. So we have to add 2 more subjects to our study in the lab or in the crowd to reach the same generalizability. So this is the gain here in samples, 2 samples out of 20. Of course, as we increase the sample size here up to 40, the gain will diminish at the end. Of course, the fundamental theorem of statistics takes over, and all the gains will go to 0. This only has an effect for the smaller sample sizes. But this is just the range where we operate. BT 500 says, take 15, 20, 25, maybe 30 ratings per stimulus, and then that's it. Okay, so here the logistic quantized metric model predicts unseen data better than the empirical model. Okay, so let's come to the conclusions. We introduced several models for the data sets of ACR type ratings, quantized metric models, and the discrete maximum entropy model. The GSD was there already before. And we tested 2 large data sets for image and video quality and found that they are statistically reliable and that they better predict unseen data than the empirical distribution is able to. So for the application might be, for example, if you want to predict quantiles of opinion scores, then if you have it in the ACR scale, then you can only, from the empirical data, you can only read off what's happening at integers 1, 2, 3, 4, or 5. But now we have this continuous curve underneath, at least for the quantized metric models, and then we can say, well, what is the quantile of participants who would rate this on the Mohs scale with 4.1 or better instead of just 4 or better, right? So this is an application. In future, we would like to continue with this, with analyzing more data sets, because 2 is not very representative. We have collected many more already, and we also have ideas of introducing other interesting models that we could compare with. So thank you very much for your attention, and I'll be glad to answer any questions.
Thank you very much. Are there any questions? Like even being co-author, I have to admit that your presentation is excellent. Francisco?
Hello. The question I have is, you had mentioned earlier that this can be applied to large population, and I wonder if you can apply this to different geography, different countries, or can you expand on the large population, and how do you model that?
Okay, so by large population, I mean the large population that the sample is supposed to represent. So you have, if you take a lab study and you invite students from a university, then probably your population will not be the entire population of the country, because there's many older senior citizens that may have vision artifacts or a visual perception that differs from the perception of students. It depends. But you could change it. Earlier today we saw the NIVD study, right? The Netflix International Video Data Set. That was a sample that was supposed to be representative of the population of 4 nations, of Japan, US, Brazil, and India. They had sampled proportionally to 3 or 4 age groups and also to gender. So that was anticipated to represent entire populations of 4 countries, but not more. So then one can, assume, if they've done their job correctly, that whatever you get out of NIVD should be representative with respect to the countries. Just like the poll for the elections in the US or in any other country were taken as a prediction of the outcome of the election, where everyone was involved, all the voters, and they were more or less correct. So that's the same here. And our prediction then from the sample to the global population is essentially something that's called smoothing or model smoothing, statistical smoothing, which is known in statistics, that tries to improve the prediction property of those empirical samples, and especially if the number of samples is small. So to alleviate these artifacts that I showed, for example, that if you have no votes for poor, then of course this probably does not mean that you never have a poor voting from all the people that you have not asked for. There will be someone who will have that vote. So if you do the smoothing according to our model, or maybe others, you will be having a better prediction of what the population on the large scale would show.
And there was one more question. At the beginning, you presented that in your original MOS data set that you didn't have much zero, yet a couple of zero scoring in the 1 and 2s, if I remember correctly. How do you deal with situations where everybody rates higher on the higher range, and how do you correct for those zeros rating? Will you smooth that out as well?
Yes, that will be smoothed out. So, for example, if you take these models that are here, these this model here. So, if you have a Gaussian, okay, the Gaussian is never zero, right? So, regardless how far you go out, there will still be some positive area under the curve. So here it is 0.039 here for the rating number 1. So that's less than 4%. So if you have only 10 ratings in your sample, you probably have 0 for the 1. So and this model then predicts, okay, there should be 4% of ones in your large population scale. So that's what what these models do. They smooth out the empirical distribution, and that will increase the prediction power of these models, and still these models statistically are valid for the sample that you have seen. And the other models do it the same way. I mean, the maximum entropy has it as a principle, right? It maximizes the entropy, so there should not be an empty cell. They are all non-empty, unless the mean is equal to 1 or equal to 5.
Yeah. Thank you.
Yeah.
Good work.
Just Mark, small comment from my side is that if you are interested in differences, for example, between countries, the advantage of using, of course, those models is that you can focus on comparing the model's parameters that you estimated from the sample rather than comparing samples directly, because we know that those models smooth the samples, so they are kind of better representation is the first thing. And the second thing, you are focusing on 2 parameters that are fully meaningful. So you can say, for example, that, I don't know, maybe in one country, the quality is right, but the spread of the answer is more or less the same. And maybe in 2 other countries, the qualities are pretty similar, but the spread of the answers is different. Yeah. So this would be kind of analysis that would be possible.
Yeah, so we did this or a similar analysis at QMX this year, and also in a new journal paper that we have just submitted, where we compare between the 4 countries of the NIVD data set, for example, and also the countries in CONIC, 10K, and CARDIT, to figure out these parameters and the differences in parameters between countries. So we let the thresholds vary and looked at the thresholds. How are they in Japan? How are they in the United States? And there we found significant differences. So essentially, the US population is more prone to give extreme ratings 1 and 5, while the Japanese does not. And this is aligning with previous findings in psychological studies that do not involve the visual quality, but other kinds of preferences. So yes, these statistical models give us a lot of tools in the hand, to estimate parameters per country or per gender, per age group, whatever, and make an analysis and compare the results between groups.
Okay, thank you very much. Seeing no more questions, we can go to the second presentation.
Okay. So let's see, then I have to first close this one and then start the other one. Let's see. Which window is it? Oh, I lost it. I have to reopen it. Oh, first I have to quit. Maybe now it's here. Yes. Okay, so, oops. Okay, yes, I think I got it. Can you see the next presentation? Yes. Okay, so this is called fine-grained subjective visual quality assessment for high-fidelity compressed images. And as announced, now we go from ACR ratings to pair comparisons or rather triplet comparisons. This is joint work with Michela Testolina, Mohsen Ginadele, who is here, Shima Mohammadi, Shaolin Su, Zhao Asenso, Touraj Ibrahimi, John Snyers, and myself. And this is work that we submitted. Okay, and this has been outcome of the JPEG ASC group. ASC stands for Assessment of Image Coding. So in contrast to the CONIC 10K data set or other ACR data sets, we are now looking at full reference quality assessment where we have a source image and coded images or slightly distorted images and would like to assess the distortion magnitude, the impairment of the distorted images. So when you do this on the MOS scale, you have the scale from 1 to 5, and it covers all the imagery from bad quality to mathematically lossless coding. However, as we know, at the high end of the scale, say from 3.5 or 4 to 5, there's little discrimination power of the ACR scale. So that range is not well covered by this technology. However, when you do comparisons and reconstructions, then you can do it on the J&D scale and get a more fine-grained assessment of quality. So there is an effort number 2 for ASC that defines a threshold for visually lossless coding, which is just a point on the physical scale of compression ratios or bit rate or so that says, okay, if you encode it at this bit rate or at a higher bit rate, you're visually lossless. And this means not that people can, under no circumstances, discriminate the coded from the source image, but this means that statistically the probability is 50% that a person can detect such a distortion at that level of the threshold here. Okay, but that's not enough to discriminate the images here above or below this threshold. This would only help us to detect something below versus something above the threshold. And so the activity, the third activity now of JPEG ASC is to define subjective testing methodologies that would work well in this range here, give us a highly fine-grained quality scale here in the assessment that's very precise and so on. Yeah, all right. So this is our job. And then in ASC4, we will look further and try to establish an objective quality assessment that would then give us the same results, in a predictive fashion. And there are not many fine-grained data sets for this quality region. And let me review a piece of earlier work of ours that defines the resolution of the full reference IQA data sets. So here's a little table of previous data sets for full reference, CRD, Live, CARDIT, TRD 2013 is probably one of the best of these. But if you look at the number of distortion levels that are applied to each source stimulus here in these data sets, you see there's only 3 to 5 for CSIQ, and for TRD there's 5 distortion levels, and they cover the whole range, usually from bad to excellent. So this is not what we would like to have. We would like to focus on the high quality range, and these data sets will have only 1 or 2 images in that range. So how densely are they packed in this range? So that's the question here. And so we can, for each image, we can define locally what the resolution there is, namely the number of distortion levels per decibel on the PSNR scale. So if like TRD 2013 has one image at for the same source, one at say PSNR of 30 and the next one at 35, then the resolution for this one image there would be 5 dBs per image. So per decibel it would be 0.2 images per decibel. So that's how we define the resolution of full reference IQA data set. And over here, you see a picture of how this resolution changes. The resolution is not a global number, but it depends locally on the PSNR that we have here. So, for the what is it? The TRD is this the one curve here, the top curve here. So this has a resolution of 0.3 here over a wide range of PSNR values. And then in our own paper about the boosting technology, we had 2 data sets where we introduced a higher quantization, a higher resolution. So we had 12 images per source, or even 30 images per source. Okay, and in JPEG ASC, so we kind of modeled the data set according to our boosting paper, and we looked at consecutive images per source that would have 0.25 JND between each other, and 10 of those. So earlier, a year ago or so, JPEG put together these 10 training, or these 10 source images that were selected for diversity of content. And we selected several codecs: JPEG, JPEG 2000, HEVC, VVC Intra, and JPEG XL at multiple quality levels. And as said, they're like a quarter JND apart from each other, which we established in a little pilot study. So the visual quality ranged from high or very high to nearly visually lossless, or 0.25 JND at the extreme. Okay, so the question now is, how can we reliably assess the magnitude of these very small quality differences in a subjective experiment? So the idea here is to use a kind of perceptual microscope. A microscope is there to zoom into the small world, and so here we zoom into the small world of small distortions. And so we have to kind of amplify these distortions, or boosting these distortions. So that's what we do. So for example, here we have a little exaggerated example of a reference image versus a distorted image. And okay, here, I don't know if you can see this after getting it through Zoom. There's, the right image is clearly distorted. In our real experiment, the difference would be much smaller. So what do we do? The first step of boosting would be artifact amplification, abbreviated by A. So we do this on a pixel level, and we look at the reference image and the distorted image and take a pixel value and RGB in this case. The difference here multiplied by an amplification factor alpha greater than 1 and added to the reference. So then we have the amplified version that has stronger artifacts by a factor of 2 per color channel at each pixel. The next part will be zoom. Okay, in addition, we can focus on the high saliency part, the most important part of the image, and zoom by a factor of 2, for example. That would enlarge the artifacts also spatially, and not just in the value of the distortion. And then we have the third component, flicker, which we already had seen in JPEG AIC. So we put the reference image in the background, and the distorted image is in the foreground. And then there's flicker. So we change from foreground to background and swap the images at the frequency of a change frequency of 10 Hertz. So you see every reference image 5 times per second, and in between the distorted image also 5 times per second. Can you see it coming through Zoom, the flicker here? I don't know. Okay, good.
Yes, at least on my side, it's very visible.
Yeah, okay, yeah, it's very visible. This is a very strong distortion. There's no problem with this. Okay, so then we created in JPEG ASC, based on these artifacts, distortions, etc. The boosted triplet comparison approach. We call it triplet comparisons because we have on both sides distorted images, and in the background the undistorted source image. So that's 3 images, and then we ask which image has the stronger flicker effect. The left, the right, or if people are not sure, they can answer also not sure. Okay, so here, for example, the left one has a stronger flicker effect, and we would say, okay, left. Okay, and now they're both flickering for the next image, and here maybe the difference not so clear. You could say not sure. So what does this give us? It amplifies, the perceived magnitude of the distortion, and in this plot here, we contrast that with the typical comparison. If we just look at the images side by side without any artifact amplification, we get the blue curve here. So down at the bottom, we have those 12 distortion levels, essentially from 0 to 3 dB, 3 JNDs. And so, yeah, and our assessment actually gave us pretty much a straight line here. Doing comparisons with, pair comparisons or triplet comparison, let's say, without any artifact amplification. And the red curve here is the impairment curve with the amplification, and this one is for amplification of the artifacts plus the zooming, but without the flicker. And so you can see here, if you at the beginning of the scale, without the amplification zooming, we would have 0.25 JND, and with we have 0.75 JND. So that's a boosting of a factor of 3. So this is the factor here. So it's around 3 here, the factor. And as we go up with the distortion level, this factor decreases, and at the end it's even less than 1. So over here in this higher distortion range, the boosting does not give us any more advantage. But here, for in the close range, very high quality, below 1 JND, we see a good artifact, a good amplification. Okay, so in our study for JPEG AIC, we used this technology, and we did both the plain triplet comparison and the boosted triplet comparison. So I showed you the boosted one where both sides are flickering, and the question is which one is flickering stronger, left, right, or not sure. And on the left side is the plain comparison where we ask the same question, or which image has a stronger distortion, but you see the two distorted versions here, left and right. And you can click on Show Original to flip or to change the images to the original. So you see the original in the background, and you can bring it up in the foreground and flip back and forth. And people are asked to at least look at the reference images once before making a decision. So then we can also have these curves here as in our previous study. So we took just 5 images from this data set. These are the numbers, and we had these 5 codecs, and each one was used at 10 bits rates, each resulting in 0.25 JND spacing, so up to 2.5 JND. And so in total, we had 5 source images plus 5 times 5 times 10, 250 distorted images. So we had to reconstruct impairment values on the JND scale for 250 distorted images, 5 contents and 5 codecs each. For this, we applied 2 crowdsourcing campaigns on mTurk. The first one was in January this year, and the second for plain triplet comparison was in June. We divided the questions into batches, and we allowed one worker to do only 2 batches. One was minimum, and then if they wanted, they could do one more batch in the same session. And we use different types of questions. We use the same codec questions here. That means we had the same source on both sides, so always the same source on both sides, and all the questions, no cross-content questions. But we have cross-codec questions. So on one side, we would have a JPEG codec, and on the other side, we would have a VVC codec, for example. So we had 2,750 BTC same codec questions. That's all possible same codec questions that are there. And then we put 20% cross-codec comparisons on top of it. We also have some bias checking questions. So with bias checking question means that the simile on both sides are equal. It's well known that there is an ordering bias for these questions. People prefer to click on the right side rather than the left, for example. To checking this, so we introduced these bias checking questions. So just to look at this. We also had trap questions where the answer was very obvious, so we could use these trap questions to reject some participants and not pay them because they were not doing their job well. So I think we had a threshold of 70% if they did not answer the 70% correctly of these trap questions, then they would not be paid. So in total, we had these numbers of questions, and we divided them into 10 batches for BTC and also 10 batches for PTC. But we used fewer questions for the PTC because they had to more interact with the system, flipping between the source and the distorted images before making a decision. That took longer, so we only used 105 questions in the PTC. So overall, we had over 1,100 subjects here. And then we filtered the subjects or the batches, and we ended up with only 630 or so. And overall, we collected almost like 500,000 comparisons, so responses to comparisons. Not all responses were provided, and some were skipped because we had a time limit per answer, of course. So a few percent were not given. And maybe one little note, but important, each question in a batch appears twice, so symmetric left-right order. So if we have one comparison, then we ask the same question again, however, with left and right reversed. Good. So how did we filter reliable batches? So for the paper that we submitted, we applied just a very simple thresholding operation. We looked at the trap type questions. We have the original trap questions, but also in this, some of the study questions were just like a trap question, so could not be distinguished. We put all of those into one bucket and looked at the accuracy of it. And here you can see, okay, a lot of people, a lot of batches here were very good. They got almost an accuracy of 1. And then there was a big hump of the distribution here with a very low accuracy of 0.5. So an accuracy of 0.5 can be obtained just by random clicking left or right. So this is like a random clicker here. Okay, and here's a picture for PTC. The PTC questions are a little more harder because there's no boosting involved, and so the distribution is not as one-sided as over here on the left. And we thresholded this just at 0.7, so this was judiciously chosen, no methodology here. And the effect on the bias question was is shown over here. Before the cleanup, we had a strong bias for the right answer, and after the cleanup, the number of answers left and the number of answers right were actually exactly equal, just a coincidence, but they were equal. So this indicates that the job of filtering was not in vain. We achieved something here. So how do we put this together now in the reconstruction? So for this, we applied a unified statistical model for plain and boosted comparisons. Essentially, this involves the following. Here on the lower right, we have the bit rate. We also could have chosen distortion in terms of PSNR or root mean square error or something. Okay, so here we use the bit rate and bits per pixels. And so we have one such picture for each source. And so there are several codecs per source, and each codec has a distortion rate function. And these are also called psychophysical functions because they map the physical quantity, so in this case, bits per pixel, into a physiological or psychological scale on JNDs, the perceived distortion or perceived impairment. Okay, so this is, and then we have that the perceived distortions are mapped by one function to the boosted perceived distortion or the perceived distortion for the boosted images. And so these scales here on the horizontal to the left and on the vertical, those are perceived distortions. They, perception operates the same on both scales. So the distributions can be modeled by the same type of distribution. We use the Gaussian here just for the like in the Thurstonian reconstruction. So they have the same sigma both on the vertical and the horizontal axis. So if we compare, say, this stimulus with a bitrate 0.8 with a stimulus with bitrate 2.6, one is for codec B and the other one for codec A, then there are these distortion rate functions. They map to the perceived distortion, and then they map with the boosting transformation to the boosted perceived distortion. And this is where we have our proportions of correct answers from our experiment, and also on the vertical scale we have it from the plane triplet comparisons, and we can then calculate the log likelihood and optimize or minimize the negative log likelihood of this whole model where these psychophysical functions and the boosting transformation function has been parameterized, and we look for the for those parameters that maximize the likelihood. So this is a bit complicated, but it works, and it gives us this unified model. We can put all of this together and in a coherent way. And this is the result of the current status of JPEG ASC3. So you see in each row here the sources. The source 02 is in the first row, the next source in the second row, and so on. And in the columns you see the different codecs, so AVIF and JPEG in the first and second column, etc. And there are several curves here. There's the boosted transformation here as the quality in JND, or let's say the impairment in JNDs versus the distortion level, averaged over all sources and all code over this one source and this one JPEG. So this is per source and per codec. So we have the BTC and then the PTC down here in the middle, and then the estimated one, the fitted model, the red line, a bit thin here. And the yellow region there is the confidence interval around the reconstruction. Okay, so this is a final, one of the final results, and this will go into the committee draft, or it is in the committee draft on subjective quality assessment, which has been submitted for the standardization under ITU. Okay, and then what's next? The next step would be JPEG ASC4. So there will be a call for proposals now for objective quality assessments next year in January, so just 2 months from now, where basically the objective is to have a metric that would predict the values that we have computed here, or that will be computed in a future study that will have to be done then in next year after the rates are in. Okay, so there the scales are required to be on the JND scale, so no logistic alignment before linear correlation, for example. So if you'd like to join this work, you're welcome. We always look for more experts to join this ASC activity. And that finishes the main part of the presentation. However, if there's time, I would like to add an appendix. Oops, there was a lot of discussion in the previous session about consistency and accuracy of crowd workers, and that was for ACR. Absolute category ratings, and this is, and now we have a similar study here for pair comparisons. I don't hear any objections, so it's only 2 slides. So it's okay. Okay. So we
Yes.
have consistency and accuracy. So what does accuracy mean? Oops, let's say, go back here. Accuracy means that we have these pair comparisons, and on one side we have a stronger distortion. We know this already. It's by construction. We designed it this way, so we know what's the correct response, and so we can say how often a subject was correct in the answer, and we can weight this according to the ease of the question. So if the question is very hard, then it is not so bad if the answer was wrong. But if the question was easy, then it should be right to account for accuracy of the subject. So yeah, we weighted the correct responses, or the number of correct responses, accordingly with the percent with the distortion level that goes from 1 to 10. Now, what is consistency? So here it's very important that we asked every question twice in reverse order the second time. And so we can now see how often were the answers for the same question consistent. So if the answer was right for the first time, it should be left for the second time. So that would account for a good consistency. If a subject answers right 2 times in a row for the same question, and on the second question, the right and left was reversed, so then that means inconsistency. If a person answers not sure both times, that would also be called consistent. So then we also weight these scores for consistency accordingly. And so now we have 2 scalars, accuracy and consistency per subject, or let's say per batch. And these numbers go from 0 to 1. And with the construction here, like with these numbers, 0.35 here, we see that a 2 or 3-way random clicker will get an accuracy and a consistency equal to 0.5. So the best performance, of course, is an accuracy of 1 and a consistency of 1, but a random clicker gets an accuracy of 0.5. What is a random clicker? A random clicker would randomly choose between left and right. Or since we have 3 options, a random clicker could also be choosing left, not sure, or right, randomly. And for both of these random clickers, accuracy will be 0.5 and consistency will be 0.5. So what we're looking for are the good crowd workers that have accuracy and consistency high, around 1. Okay, now what did we get with our 470,000 responses? So this is the boosted triplet comparison study here. And the top left view is accuracy. So this is the accuracy going from 0 to 1, and this is the history over all the batches. For each batch, we had an accuracy. And you can see very clearly that there are 2 distinct populations of crowd workers. Those that work well with a high accuracy, and those that work poor with a low accuracy, around 0.5, which you can attain with being a random clicker. What about consistency? Same picture here, or similar picture. You get 2 distributions, or this could be very well modeled as a superpositioning, a mixed distribution of 2 individual populations, a reliable crowd worker population and an unreliable one with a consistency of 0.5, which you get if you just randomly click or always click the same answer. Okay, so since these look very much the same, we thought, okay, we should maybe split them up. Not split them up, but join them together. Take the average, half accuracy plus 1/2 consistency, and this is the result then. And you can now see, again, clearly these 2 populations, and then we used Otsu thresholding to find out the best threshold down here that would statistically separate the two populations. And then the left side would be discarded as unreliable data, and the right side would be accepted as reliable. If you look at the scatter plot of accuracy versus consistency, you get this very interesting graph on the upper right. So consistency from 0 to 1 on the horizontal axis, accuracy from 0 to 1 on the vertical axis. You can see the good crowd workers up here in the upper right. This is where accuracy and consistency is large. Then you have a big blob in the middle, 0.5 and 0.5, accuracy and consistency. Those are the random clickers, or equivalent to random clickers, right? They don't perform well. This is data that is essentially useless. It's you don't want to have people in there that randomly click. But then there are other effects, like over here. What's this to the left? There are these spurious batches here. They have an accuracy of 0.5, but a very low consistency. Accuracy of 0.5 means half of the time for the right. Consistency 0 means, they do not consistently give the right answer or the wrong answer. They're inconsistent. These are the line clickers. So if someone always clicks left, 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 the accuracy will be 0.5 and the consistency will be 0. So these are the line clickers that always clicked on the same side. Now down here at the lower right, also interestingly, what is this? These are subjects or batches where the subject has a large consistency, so this is not so bad, 0.8 or so good. However, the accuracy is very low, so they consistently gave the wrong answer. So these are the people that misunderstood the task. They clicked on the wrong side of the answer. So they probably got the perception okay, and they concluded everything correct. Only they misinterpreted the question and hit the other button. Yeah. Okay, the last slide here, the last image here shows that there's this is consistency and accuracy averaged, and on the vertical axis is the mean response time. And here you can see also a clear distinction between the reliable crowd workers over here with a high consistency accuracy and the unreliable one over here. This is a lower batch blob that says, okay, for those unreliable ones, the mean response time was only 1 second. The people who gave a good answer, a reliable answer, had to think 4 seconds before they could give their answer. So that's another indication that our thresholding seems to be working well. So in the end, from this scatter plot here, what we're proposing is this also thresholding. Then in the scatter plot, it's a diagonal line here. And so we have the well-performing crowd workers and batches up here, and the rejected population down here. In addition, we will be activating some outlier removal technique that removes the most unreliable of the good ones here. And so that's the red diamond-shaped batches. They could also be removed. But we have not finalized these studies yet. And then this is the same picture, the same scenario for the plain triplet comparisons, where it was a little harder. And I will not go through the details here, but you can just look at it. So thank you very much for your attention, and I'm sorry for taking over time if this has happened. Of course, we can go to questions.
Thank you very much. Very interesting study. I see a question, so please just go with the order.
Yeah, she.
So Z is first, yeah.
Hi, thanks for the great presentation. Good to see an advancement on the comparison-based methodologies. So I have a few questions, but just some quick ones first. How do you see this method extending to video-based test? How well have you ever tried it out? That's the first one. Second one is, what if I want to collect some local information, for example, like which are the part of the images that contribute to the biggest, the most salient distortions? Is there a way to measure that as well in this framework?
Okay, so two points. So first for video, yes, one can do the video testing also, and we have tried this out already. There's one paper that we have already published at CSVT with Mohsen as a first author. Yeah, how would we do this? We could probably display the videos rather not in side by side, but sequentially to have the full resolution. And also, we could do this with the images if that is objectionable. We had it, we had the Zoom version on half the screen each, and but it would be maybe better to have the Zoom version going up to the full screen and then have it one after another. Yeah, so yes, for video one can do this, but with the boosting, we are not quite sure how well it works. So our experiences are mixed, and at this point, I would say, yeah, if you want to apply the boosting, you have to be careful. The boosting with the flicker, let's say, okay, what's the flicker for the video? You would then change from the distorted to the undistorted video within running a video. I would say maybe 5 frames original and 5 frames distorted. And this will work not for all contents, so there will be some issues with it. So maybe it's better to just have it sequentially with running and then compare it in this way. So yeah, one can do it, but it would be it has more issues. And the salient parts, okay, can we find out which parts are more salient? So I suppose you mean that in an image there could be some artifacts that are more visible because they are in this, or the artifacts are more salient in some region than in another region. Yeah, for this we have done a study already for images where we also used the flicker test and asked the subjects to identify the 3 positions where the flicker became most obvious as you increase the distortion parameter. So we had a slider for the distortion parameter, or say the JPEG, the JPEG factor there, and then the subjects use the slider to find out, well, where do I see a distortion? And then when I see distortion, they pointed out to the 3 locations where they would first see a distortion. So yeah, that can be done, and we did it, and it has been shown at QMAX 2 years ago in Ghent, and yeah, but it's not. Yeah, but it's not accessible through the JPEG ASC methodology. It was not designed for that purpose, to find out where it is. Right. So we also had.
Thank you.
Yeah. Mm-hmm.
Lucas?
Yeah, thank you so much for the presentation. I'm really happy you also added the appendix, because that was really enlightening. I think it's a great analysis. I have more of a fundamental question, and that is that if I understand correctly, we basically are within the range of 1 GND. That means that most subjects will not be able to see the difference unless it's boosted, right? So when we are using the boosting to artificially make the differences that wouldn't be visible. And my question is mostly, is there an added value of doing this compared to, for example, just saying that if we are within 1 JND, the PSNR is the differentiating factor there? Because I can imagine that we can design a boosting that is going to make any difference visible, which sort of takes out the perceptual system from the equation to me. So I'm just really trying to understand what's the added value here to scope into this compared to if we just took a difference in that space, because we know that people still don't see a difference anyway.
Yeah, very good question, Lucas. Thank you very much. Actually, that's the purpose also of the JPEG ASC4 that comes in next year, where we're asking for objective methods to reproduce the values that we see here for subjective ones. And then it may well be the case that we will find, okay, these objective methods are so good, they can predict the values so well that we don't need any more subjective experiments in this region. But this is an open question. We don't know yet what will happen. And okay, the other part of the question is it reliable if we amplify at such low distortion values? That's a valid question, of course. And my personal take on this is that, yes, it is reliable unless you do the boosting so that it goes through the ceiling, right? So if you use an amplification factor of 5 or 6 or so, then things become highly nonlinear, and also your boosted color values will be way above 255 or in the negative, and you have to clamp, and then you get these problems. So we aligned it to just 2.0, and the clamping will appear only in a very few % of the pixels. So as long as you're moderate with with your pushing it, don't push it too hard, don't push it over the limit. Then I think we will do just what a microscope does for the biologist. If you turn up the microscope too strongly and put too much light on your object, then also your results will be not valid anymore. So yes. Yeah, I think also the results that we have from our data analysis. Let's go back to the slide here. Say that down here at the low end things become fairly linear, right? So there's not much to be done here. So we can probably do with just a few points here. And then extrapolate linear. So we would not recommend subjective testing methodologies where we will ask for 0.05 JND or 0.01 JND, although it could be done, but it's not necessary. And that's probably the point that you are saying, that down there things become linear, and you could just use also some simple objective metric and scale it so that it is translated into JND units. I'm sure we will see that next year when the contributions of JPEG ASC4 will come in.
Yeah, looking forward to seeing those. Thank you so much, Dietmar.
Yeah, thank you, Lucas. Johannes.
I think Francois was ahead of me. Francois.
Oh, Francois. Oh, yeah.
Francois,
I cannot hear you.
Muted. You're muted.
Yeah, I'm muted, sir.
You can go, Yanis. You're the new co-chair.
That doesn't give me any special privilege.
Exactly. I not allow it. Francois first.
Okay, in your opening slide, you had shown the difficulties in what you call, I think, in mass 4 to 5. You said the granularity was not precise. Can you just expand on that slide, on that problem, and again, how you're solving it with? Is it you're solving it with your boosting and triplets versus the traditional ACR? Is it how you're solving that problem?
Yes, that's the approach. Okay. I could show you some images or some results of studies where they have used the Morse scale and compared it with the comparison type of scale for the same images, and then they showed that there is a saturation effect. So that means on the Morse scale, from 4 to 5, when you compare it to the JND scale, then at the higher JND levels, the Morse does not change anymore. So that's the saturation. So when you're at 4 or 5, then the numbers bunch there. But when you look at pair comparison, which is more sensitive, and you can see differences more clearly in that range, and you scale it according to Thurston, you do see the fine differences. Okay, so the resolving power of comparison studies is larger than the power that you get with just single stimulus assessment using a Morse scale, or also or using an interval scale. And that has been confirmed by other studies in a few papers. For example, by studies from Cambridge University, Raphael Mantiuk's group, they have seen this, and we have seen this, as I mentioned, just in JPEG, where they looked at point cloud compressions and perceived qualities the same way. So yeah, but I don't have this figure on my
Okay, no, that's
desktop
fine.
here right
I want
now.
to just thank you. I wanted to confirm that I got that part right. And maybe my second and last question is, when you do this comparison with your boosting methodology, are you showing two boosted images, or you're mixing them with the regular ones, or how do you arrange your showing of images?
It is this. This is the typical question for a boosted triplet comparison. So we have on both sides, we have a distorted version of the same source and the same zoomed part of it, and but different distortion levels. So the distortion level could be 7 on the right and 8 on the left. Okay, and they are flickering, so they're alternating with the source image. So the amount of flicker, the flicker effect is proportional, let's say, to the distortion that is in these images. And now the question is, on which side do we have the stronger distortion? That's a comparison. And if we say, okay, the right side has a stronger flicker effect, then that means the person has perceived that the distortion on the right is stronger than the distortion on the left. Aided by the boosting techniques, that is by the artifact amplification and by the zooming and by the flickering. So there's a triplet question, right? So we have 3 images are involved here: the 2 distorted and the reference, the source image.
Okay, perfect. Thank you. Very good work. Impressive. Thank you.
Yeah. Thank you very much.
Thank you. Guys.
Yeah, and thank you, Dietmar. I always enjoy the work. I'll just pound a little bit on the point that Lucas touched upon, right? We all understand that going back to the, psychovisual perception experiments, that there is a around the threshold type of experiments, right, where you're presenting stimuli and you're trying to determine at which point it is visible, not visible, and then we go supra threshold, right, to understand how much more visible is something, right? I have a feeling that the boosting is really shifting things that are below threshold, obviously, into that region. And I'm not sure if the translation factor there, as you claimed, right, there is this analogy, is really giving us, allow me to use the word, useful information. I'm not doubting that the experiment works. All I'm trying to say is that if 2 people cannot see a difference objectively, giving them a magnifying glass and asking them, can you please check again? Can you tell me what's the best? What is truly the value there? In other words, in which practical scenario this will help A versus B?
Well, if there's some small print and some elderly people who cannot tell whether this is a 5 or a 6 on the paper, and you give them a magnifying glass and they both agree it's a 5, then I think there's some information gained, and it's the same here. Yeah, so the magnifying glass is working both in microscopy and also here. What you may be concerned with, but I'm not quite sure if this was the question, is so on the boosted scale, the difference is large here. And so what do we gain? Well, this is not what we report. What we report is the small scale difference here on the regular scale here. So this is only 1 JND and not 2. So these two stimuli are almost, well, not almost, they have 1 JND difference in this case, so it's quite a bit of a difference. But if you move the black and the blue dot closer together, or the blue one over to here, so that the perceived distortion is almost the same on the normal scale without the boosting, then after boosting, the difference becomes here about twice as large. And that could be distinguished then statistically when you ask 10 or 20 subjects the same questions. right? And so our model then takes all the answers to all those hundreds of thousands of responses together and reconstructs then this model. And what we report is the small difference and not the large difference here. So yeah, yes, we do get information for the boosted stimuli more easily than for the plain stimuli, and we merge this information in a statistically meaningful way with this boosting transformation that we estimate to come up with small scale differences of fractions of J&D units, and that's statistically reliable. So we will figure out like what is the effect size between these distributions here that we have when we use our technology, and then what we would get if we use only the traditional technology, which is only the right square here. So side by side comparisons of two stimuli, and then reconstructing it on this scale, and then the effect size will be much smaller. We have not calculated that yet, but we will.
Yeah. And also, just maybe another thought here. In most practical services, the difference when it comes to the high end of the scale are not only not visible. I mean, we're arguing here whether you're going to take small differences and make them larger so they're amplified. And you can debate whether this, I can probably accept that this is a valid scientific way to do it, but coming back to the objective of this, right? So people have been having a hard time, honestly, accepting much bigger differences as making a meaningful impact in the way that they consume media, right? And there is publications around this acceptance and annoyance level where there's almost a sigmoid between, let's call it now, MOS in the classical way, ACR 1 to 5, and whether someone uses that higher quality to either enhance and watch more a certain video, or whether the level of satisfaction they take is changing, right? So when you really try to say how much that MOS in the high-end range, where it's where we are amplifying here, matters to consumers, there is increasing evidence that unless you're talking about experts and people who, for example, are the creators of the video, right? Or somebody who has it as their job to be a critic, right? But for the overwhelmingly vast majority, once you reach a certain level of quality, that higher end part of the range is much less relevant. So while I admire the scientific approach, I don't have anything to say against it. I'm trying to understand how much practicality this will bring to services that use either image or video compression to do their job.
Yes, this is a good question. Of course, the quality that you can transmit or how much it will be appreciated depends on many factors. Foremost, technological factors. What is the screen size? What is the resolution? How many pixels per inch? What is the bandwidth that's there? And of course, in some situations, the quality can be reduced by a lot because the technological aspect there will prevent the high quality from being appreciated. Also, it depends on the content. So if you just want to know how does the restaurant look like? Where are we going for dinner? You're not interested in the high quality. You just want to look. Is it a nice, cozy atmosphere there? And does the food look good? Okay, and that's it. Or if you just want to, figure out some information, which is more or less verbal or so on, you look at some images to find out. Then it does not really matter whether it's really super high quality. But of course, there's other applications when you're watching a video on the couch and you have invited your friends, then you would like to have a high quality. If the picture is a bit fuzzy or so, this doesn't look good. And of course, technology is going to advance. So now we have high quality monitors available, very high resolution, but few people can afford it. But maybe 20 years from now, or 5 years from now, even more people will have it, and it will allow us to see the high quality. and then this might become very relevant.
Yeah,
Right.
I would probably use, if I may interrupt you, another example, which is the medical profession, right? There are specific applications where I can 100% see the value, but again, when it comes to media enjoyment, and actually I argue that the resolution and the density of the pixel doesn't matter, because it's the physical distance that dictates what you perceive. But again, I don't want to derail the discussion. It's not a question.
I'm really sorry. I hate it, but I have to cut this discussion because we've got only 40 minutes and still two.
Lucian, one sentence, please. Just one sentence, please. The main part here, impact, is for codec development. This activity of JPEG is called assessment of image coding quality. So codec developers, they care about the quality of the codecs. They want to optimize the codecs to give the best performance, and this is where this will be applied, and not so much in consumer delivery of consumer video or consumer data to will not be used for streaming so much.
Well,
okay,
I personally see lots of places where it could be used, but of course, well, Yanis got much better point of view, being on the industrial side. Margaret, please.
Thank you. Dietmar, very interesting. I'm especially inspired by the last two slides. You said, well, if we have time, because it links back in, we can handle this by email instead, but I'm curious, if we reduce the ACR 5-point level scale to a 2-point scale, good or bad, do you think the clear separation you saw with pair comparison would still be able to be detected? And
yeah, well,
right.
You're talking about the clear distinction between the reliable and the unreliable workers. Is that what you mean?
That is.
Okay, so this study was for comparisons, not for ACR studies. So I don't know how this could be how this could be translated into the ACR domain. That is going to be very difficult. I mean, one thing, first of all, is that we had each question asked twice for consistency. Of course, this could be also carried out for ACR, and I would highly recommend that. But most studies have not been doing that. So we cannot a posteriori analyze ACR datasets for this type of consistency. The consistency that was addressed in the previous session by Lorik was a different consistency. That's a consistency assessed by statistical models. So it's a spread of the answers of a subject around the consensus. But here we have a consistency of, at the question level. So, but that could be done. And maybe you could also design questions that would assess the accuracy of the responses by giving them high quality stimuli and very low quality stimuli, where you would expect a rating of 5, respectively 1, and then you can count how many did they get right. And maybe you can also make this sort of more continuous with a weight factor or something. But it's a little more difficult than for pair comparisons. It can be done, but it has not been done in practice as far as I know.
Okay, thank you.
Thank you very much, Ms. Scott. Your hand is still up. Do you have any other questions? Okay, I guess not. Okay, thank you very much. And we should go for the next presentation, which is by Shell.
Okay. So can you see my screen?
Yes, we can, so.
Okay, great. Thank you. So this is a bit of a mixture of things, but we participated in the cloud gaming effort. We have been looking a little bit on the experiment, and I was playing around a little bit with the bootstrap, and I think all this will be about that. So the change, right? Yes, right. As I said, we participated in this effort for developing objective quality models called parametric bitstream-based quality assessment of cloud gaming services. That is an ITU project where they try to develop a model for that is divided into an interaction quality model and a video coding impairment model. So they have had an experimental campaign with different lab, different parts of the world to collect data. And we participated in an experiment evaluating the video coding impairment module. And I started to do some analysis of the data we got, and I did a little bootstrapping on that. So this is a work in progress, and I will not get into the presentation of the overall result because that has been done before and probably done more completely. So I just have our, let's say, part of the experiment available. So the method for the experiment was a passive test where a number of conditions were contained. I mean, they used different codecs with different bit rate, different resolution, and different frame rates, and a large number of also sources. And if you cross all these conditions, you will get a huge experiment. And so they produce, I say they, because I didn't really participate in this part of the work, 16 databases with 90 processed video sequences in each. And of them, there were 5 with HD with frame rate 120 frames per second, and 11 in 4K with frame rates between 30 to 60 frames per second. And we had one of those databases. And the procedure was that as kind of classic video quality experiment, we invited test persons to the lab. They signed a consent form, and they were informed that they could stop at any time without giving a reason if they were suffering any negative consequences. They were given the instructions to read, and we had a pre-questionnaire that was filled in. We tested the visual acuity and color vision. The test person were invited to the test room, seated 1.5 H, so there's our screen height from the screen. That was about 1.2 meters. We presented on a 60-inch OLED TV display. Then there was a training session consisting of 5 videos, and the main session of 90 PVSs that was then scored. The scoring was done on the scale shown here in the picture, and I think that was all I was showing. Kind of gave you interesting results, especially for a usage of the full range of the scales between bad and excellent. So it was a nice idea. I haven't used it before. It was experience. And then we ended with performing a short interview with the test person. I will not cover that in this presentation. So the test participants, there were 26 test persons. They were equal number males and females. The age varied from 1959 with an average of 32. And there was a varying degree of skill levels for the participants for gaming. So the analysis, one of the challenges we have is to decide on the analysis method to go for. And as usual, one can try to check if the underlying distributions are normally distributed, as we did, and then the questions come up what to do. Should we go non-parametric? Should we go parametric anyway? And so on. So I started to look into the bootstrapping approach. So if we need a bit digression on this. So what we have been looking for into the bootstrapping, perhaps this is well known for many of you, but we looked at how the effect of to the MOS and the confidence interval, the shape of the distribution, and the normal test result when you do a hypothesis test, but also the V statistics for that we will. So then I will show a little bit the result from the actual test, so to speak. So just to remind everyone what bootstrapping is, if you are not familiar with it, so it is a technique to estimate the distribution by repeatedly resampling the data, and it's good to understand the distribution, especially a non-normal one. And the original sample is small, and the assumption of the underlying distribution are not well defined. And the idea is that we more or less end up with a normal distribution at the end due to the central limit theorem. So, and in our case, this is for one of the results where we didn't have a normal distribution to start with. It failed on the Shapiro-Wilks, and then we did the resampling for 1,000 times, and we can see that we end up with a let's say distribution that is more like a normal distribution, though not completely, perhaps. And then if we, as another example, and what I wanted to show here is that at least one could imagine that one lose a bit of an information with this process, because in the original distribution, which is green here, there is a tendency that there could be a binomial distribution, and that will be, at least in this case, disappearing in the resampling process. I haven't done a lot of this investigation to see if this is always the case, but it's likely that when you do a large number of resampling, the main peak or the main part of the distribution will be the dominant one after the bootstrapping. Here I wanted to show a comparison between if we calculate the mean opinion score and both bootstrapped and non-bootstrapped. And we can see that there is a very close relationship between the mean values and the for all of the PVSs, with a slightly shorter confidence intervals for the bootstrapped results. And so in a sense showing that at least with this data, even if we didn't have fully normally distributed data from the beginning, it seems that even it is stable under the bootstrapping operations. And also, what was a little bit interesting, I would say, was you would imagine, at least naively, if you bootstrap and you go for you have something that has been tested to be normal to start with, you would get something that was normal after the bootstrapping operation. But several of the tests I tested, actually the p-value from the test, the hypothesis test, was actually lower after the bootstrapping than before the bootstrapping. So, and the explanation for that is that in most cases the hypothesis test for normality becomes overly sensitive to deviation from the normal distribution when you have a large number of samples that you get when you are bootstrapping. So this may not be the best to look at in this case.
Oye,
So
una
one could-
pregunta, Julián, muy rápido.
One
no.
could, of course, look
Tú nos enviaste los 4 artículos.
at the shape, the QQ plot, or something else to convince oneself that it is more normal. What I looked at was the Shapiro-Wilks V statistics, which is the underlying statistics that is calculated when the Shapiro-Wilks is when you're doing the Shapiro-Wilks hypothesis test. And these statistics will be closer to 1 when the underlying distribution is closer to a normal distribution. And as we can see on this graph, which has the V statistics on the y-axis and the PVS, I would say that the PVSs that were tested as non-normal after both bootstrapping and non-bootstrapping. And we can see that the test statistics goes very close to 1 after you do, in this case, also 1000 iteration in the bootstrapping procedure, which would be an indication, but not a proof that we are having but a good indication that we are very close to the normal distribution. So then, just going further with let's say the more regular results from the experiment. I did a histogram of votes, and it was a 7-level scale, which you see here to the left. You can where you have the number of votes on the y-axis, and you have the scale number on the x-axis, and you can see that it's not a let's say an even distribution for usage of the scale, but then the end point of this scale is actually given let's say that something is really bad and something is obviously very, very good. So what I did was I added the 1 and 7 to 2 and 6, and in this case the distribution becomes quite even, and I think that's a good indication that this scale is working as intended to actually get people to use the full range of the scale. And then I did the plot of the mean opinion scores on the y-axis and the log bit rate on the x-axis, and I thought it was interesting. Maybe this is also well known by everyone that we got almost a linear relationship here, and with a very quite good correlation. So as a first, let's say, approximation, just taking the log bit rate would give you a very good indication on the quality that you would receive from the videos that you have. And coming to an end, so well, one more on the slide. I was surprised it disappeared. But so for this, let's say, limited study, I think that the bootstrapping can help making data more normally distributed, and that's more of an extension of the method in itself. The hypothesis test, not only Shapiro with, I was testing Anderson and a few others. They have the same behavior. They will be probably overly sensitive to the deviation and will probably also give you that the distribution is still normal. Not normal, I would say. So looking at the V statistics, for instance, QPro plot, the shape could be another approach to actually check that you have got what we were looking for. But maybe some nuances of the Oranian data may get lost in the process. I haven't taken it too much, but there were a few examples, one that I showed you. Then for the data from the actual experiment, I think the score of the test persons were quite evenly distributed, and also the MOS was quite linear to the log bit rate with a correlation of 0.84. Thank you. Okay, I see that I have a question or a comment.
Yes.
Sorry, I was muted. I just asked Yetmo to ask the question and unmute, but I didn't unmute myself. Sorry for that.
Yeah, I just have two quick questions to better understand what you were doing. At the beginning, you showed a scale for the responses, which was continuous from extremely bad to excellent. And you had tick marks there, and the tick marks were also labeled from bad to excellent. So it looked like a continuous scale where people would give you an answer. And then later you showed discrete scales, so 5-level and a 7-level discrete scales. So I was wondering what actually happened, and then maybe you could show a histogram of on the continuous scale how this was done. I remember the NIVD study used a similar continuous scale, and it had strong peaks at the major tick marks, namely at those tick marks where the labels from bad to excellent were written. That was one question. The other question is, you explained the bootstrapping very nicely, and you said after each bootstrap sample, you calculate a statistic, and that goes into the evaluation. But you then, when you carried it out, you didn't tell us, or maybe I missed it, which statistic you calculated. Was it the MOS, or was it this normality criterion, or what did you do with the bootstrap sample?
Okay, for the first, you're right. The scale were more. I mean, they could give
Yes.
Scores between these, and what I did with the histogram was to group them into these groups of the categories. So maybe, as you say, a more continuous histogram would have been better to show. Yeah, so I agree in that. I bootstrapped the mean opinion scores and the confidence intervals, if I remember correctly, program.
Right. Okay. But then yeah, the picture where you have the green and the blue, the green and the red distributions, picture 9 and 8, there you're showing the moss as it was bootstrapped. So the bootstrapped mosses were in the red shaded area, and the green one, well, that was the empirical data. There you would not have a distribution, but only one value of a moss, wouldn't you?
Yeah, you're right. Maybe I went through a number of different versions of the program. So at this point, I may just have redistributed the actual raw scores. Yeah. So
I see. Okay, and then the moss of the green part, the empirical data would probably be very close to the maximum of the distribution of the bootstrap mosses, as you have shown in this diagram. I think number 10. That's where you have that the mosses and the empirical mosses and the mosses of the bootstrapped samples are almost the same, and that has to be expected. Of course, that's natural. That anything else would suggest that something was wrong in the calculations, I think. Yeah.
Right.
Yes. Okay. Yeah. And so the confidence interval for the bootstrap were probably assessed using the 95% confidence intervals from the 1000 bootstraps, and the confidence interval for the moss was using one of those estimation formulas from the empirical data. That's what I think you have done. Yes, and that agrees very well. So that's comforting that you get consistent results there. Yes, thank you.
Thank you very much. Margaret, please.
So this is a quick comment. Shell, very interesting as always. And your slide 13 showing that the scale did what it was intended to do, that was really interesting. So thank you for that in particular.
Okay, thank you.
Jans. And
Dietmar, I think that's an old hand of yours.
Yes, this
yeah, so Dietmar covered my core question on exactly what was the statistic that was bootstrapped. So now I have a much clearer review of the presentation. So back on your log plot, the linear plot, is that all codecs put together, or you picked one of them like AVC to plot this?
That's all codecs. Though for all the data, all the PVSs.
Yeah,
but just for our part of the test, our 90 PVSs. So it would be interesting to do this log plot for the whole data set they have in this cloud gaming experiment, and see if it still holds, or if it was an anomaly of our 90 PVSs.
Yeah, this is very much in line with my experience, right? So, and that was the main rationale behind having the famous, BD rate beyond the guard delta. I contend that if you split your PVSs per codec, you're actually going to see 3 lines. They're going to show up over there. So what you're seeing is the combined effect of, because I thought I saw, did I see correctly that you use 3 different codecs, AVC?
I will show you again.
AVC, HVC, everywhere. So I do expect to see a nice separation among the 3, and in particular, when you do that per source, you're going to get even nicer and cleaner, perhaps. But this is just a comment very much in line with my expectation. Thank you.
Okay, I will produce those plots as well. So thank you for the suggestion.
Thank you very much. Okay, so this is the end of this presentation. Don't see any other questions now. I have a presentation about the future of SAM, and the problem is that we do not have much time to actually discuss it, and it's clearly showed that I didn't protect SAM session enough to. But I'm really bad in stopping the discussions. Anyway, I will try to go very quickly through the presentation that I created, but we still should have a time to discuss the future of SAM. So just in case we don't have this time, then we'll move it to the next SAM audio call. But here there is a chance to discuss it with a little bit bigger group. So first of all, current description of SAM, and I extended this current description with what is the mission. So improve analysis method and understanding of subjective experiment, and we have results here. But the second mission point is improve the statistical analysis of objective media quality predictors models. And here I'm afraid that the SAM didn't do much. Yeah, we discuss it, but we don't have the let's say new results. Yeah, I'm chair, so this is all copy from the website. I'm chair for a long time. Maybe it's a good moment to change. So it's also kind of put to this discussion for us, and we would probably like to change the website as it is described. So my proposal is to move the document and the software section from working methods. Maybe we leave document with the working method, but maybe we have another section with software, and then it's kind of more visible for the others. It's a proposal. So let's maybe I will go through the website to the end, and then we can discuss it. So then the current description of the goal of the SAM, we've got the short-term goals, where there was this maximum likelihood estimation. This is done, so definitely we have to change it from the short goal point of view. We've got a midterm goal where there was publishing ITU recommendation, which was done, and this is excellent. And the white paper, I think that this white paper, maybe it's even better idea that Margaret said, like this tutorial, how to use the method, so then it could be more widely used. And the long-term goals, we've got this improved methods to use, draw conclusions for subjective experiments, and definitely we did some progress here. Of course, this work cannot be finished probably ever, so but we did something. Understanding the processes of expressing opinion in a subjective experiment. Here, I doubt we've got so strong results. Yeah, and this is probably something that we could extend and better understand. Improve subjective experiment design to facilitate analysis and application. Well, we didn't propose. Well, the work that Dietmar showed is definitely proposal for the improvement of the quality estimation, especially for the highest end. So in this sense, some got some progress through Dietmar works. I say we didn't propose in sense we didn't push it into standards, but maybe it's not the only way we should like extend our work. So this is no changes proposed is maybe too strong word, yeah, because there are changes that are proposed by the people working within the group. And improve analysis of objective metric performance. This because before the group started, we already had this analysis proposed by Lucas and Margaret. So we just discussed that this would be nice to have them to compare them, but actually no comparison was done. So definitely we need some changes here. So we need new short-term goals. We need new midterm goals, and thinking about the long term. I will go to it further. Then we also got this uniform JSON, and I think that it didn't really catch up. So we've got some work done, but it never was widely used. And I think that a little bit problem was what Yanis said, with the generative AI. I really like it. We should start slow. With this work, we really try to cover lots of different experiment design, and at the end, it was too complicated to really easily use it. So probably, I don't know, we could kind of try to step back and, there is at least some work done in the JEC hybrid to use a lot of data sets into the JSON file, the Netflix JSON file, and maybe we could just move this direction and then maybe come back to it in the future if we start to include more things. So this is about the website. Any comments? Any ideas, like quick comments? Okay. If not, then I extracted the conclusions from our discussions. Yes, we've got the comment.
Zero is his hand.
Yeah, Lucian, so on the SUJSON front, I think one of the related project is the E2Nest subjective testing platform, which also encompassing data format. I wonder if we could just maybe substitute this effort with that one, because I think it's already have some momentum. I don't know if many people is aware of that project, so it's not being like well advertised. But there's a presentation we did, I think a few VQEG meetings before, just in case people are interested in to continue this initiative and further contribute and make it into a better shape. I think we could continue with that initiative within the SAM scope. That's what I want to say.
Very good idea, definitely. Yes, and this would also make the software section more reasonable, because this would be not only linked to Serial but also to this project, which looks always better. Okay, then from the conclusions, we discuss a lot about the pair comparison, and because we developed to some extent a lot ACR models, and especially the work that was presented today by Dietmar, this is really considering lots of different models, but we do not have model for the pair comparison as such. And again, comparing objective metrics and extending P1401, this was discussed, and how to combine multiple data sets. This was then returned on March 4th and March 25, 2024. So this was the discussion that kind of come back. How to test any new statistical methods. Again, this was something discussed in February 2024, that maybe we should be able to present, like, if you want to have a new method for analyzing data sets, then please show us those statistics to prove that your method actually kind of works. Again, this objective metric analysis compare Margaret's proposal with how to compare different metrics and Lucas, which are very similar. And probably we could extend like one method and then try to push it to 1401. Then the next call was more about the industry applications. So this was using confidence interval to draw conclusions about specific video codec configuration, and especially BD rate analysis, using again confidence interval to draw conclusion about one objective quality metric versus another, and culture independence things. So this was pointed like important topics for the industry partner. There were also two less well-defined problems. So analysis difference for the viewers that are very picky. So we are now focusing on an average viewer that quality is not very important for them, but of course, for some services, it would be also good to focus on some people that are very, very focused on quality, and average is not enough for them. and then you need specific metrics and maybe specific system of doing subjective experiment. Multi-screens, this was brought by Z, but from like Microsoft, so the teleconference as we have right now. And again, pair comparison and statistical methods, how we can combine it with ACR. Then on October, there was perceptually lossless metrics. So again, a topic that is to some extent, in my opinion, addressed by Dietmar today. So at least from subjective experiment point of view, what we could do to get information about how to estimate metrics which are nearly perceptually lossless. Color distortion, subjective testing for generative AI. It's a topic that it seems that another group will take, and outlier removal. Those problems were kind of pointed. So this is like historical discussion. I tried to combine it with some groups. So we've got theory development, which in my opinion, there's no doubt that this group worked and probably we will continue anyway, because we've got certain momentum. And from the theory point of view, there is still, well, further development of subject model for ACR. Well, we already work with Dietmar on that, so definitely there will be some progress. Then better understanding of pair comparison and the relation to ACR. There are papers, there are some results, but maybe our group could kind of try to compare it. As far as I remember, most of those models assume that underlying is a normal distribution. But if, for example, we show that logistic distribution is a better model for ACR, then maybe we could kind of try to see what are the consequences of changing normal to logistic, and then how pair comparison data change to the ACR data. For me, comparing ACR to PC to pair comparison, still between content, I know this data. I have the data from subjective experiments where we show that actually they can reverse. So ACR showing the A is better than B, but if you do pair comparison, you will get the opposite results. And this is especially if there is a color distortion or some things like that. So this would be interesting analysis. And multiple distortions. So we are now mostly using data sets that got like single distortion, like only compression or compression and scaling. Those are kind of, yeah, close. Okay, I see that people have to drop, and I'm wondering if this makes sense to discuss, especially like if Yanis, you have to drop, then you are one of the co-chair of the group. So discussing about the future of the group without you probably doesn't make much sense.
And my deep apologies. It's just that the calendar was already occupied with an important call. But if the group agrees, thank you for this. Is very detailed, and I really think that there is a lot of meat here. I suggest we invite the rest of the group, meaning not only the SAM people, to join us in our next SAM call, where we can pick it up exactly at this point. This is my suggestion, if everybody agrees.
Yeah, I would be happy with that, because yes. We basically the meeting ended like 3 minutes ago, so we will then leave only with those that can extend the time, and this definitely not for all of. Margaret, I see your hands was raised. But she's not in the call. No, you are.
I was going to suggest just quickly jotting down ideas from people who aren't likely to be at the next SAM meeting or who might forget their idea between now and then. I agree, continuing discussions at the next SAM meeting would be best.
Okay. So maybe I will finish the last 2 slides with the limited number of people, and then we can come back to the discussion at the next SAM meeting and collect any feedback that we can get right now. Okay. So then perceptually lossless metrics, this would be interesting topic. definitely we've got momentum. We've got work by Dietmar, and some people were interested in this topic. The new subjective methods going away from quality and how to analyze, especially because the moment we don't ask about quality, the analysis start to be tricky because we start to collect very different type of data. And this is definitely interesting. New testing, looking at specific product and include different dimensions like how much the content fits a user, understanding the relation between quality and service as a whole. Here I've got an interesting impact. Actually, I would love to discuss it with you, Yanis, but as you don't have time, then let's move it to the next SAM session. Because after our last SAM session, I've got very interesting insight from a person working on psychology and how brain works, about if quality is important or not. Okay, so our to-do, and this what you could do to kind of prepare before the next session. So list future problems. I did something in the presentation, but maybe you would like to add something new. But especially think about who is interested in doing something in the specific topic. Yeah. So maybe we could even kind of make a list or put into the document the problems that we would like to solve, and people that are tentatively interested in the topic, but maybe more like people that are really working on certain topic and do some progress. Yeah. Then it would be easier for a newcomer to, for example, let's say that Bartłomiej is my PhD student. He's interested in this work that is presented, let's say the nearly lossless compression, and then he knows that he should go to Dietmar to get some more information and maybe join the workday. Definitely update our call pass website. This definitely we have to do. And if I collect if you have some inputs from the points that are sent in this presentation, please send it to me. And then for the next SAM session, I will update the presentation with the idea how the website could look like for the future. So we don't have to do it at the meeting itself. And I propose to review the progress of each meeting. So we didn't review the progress of SAM. This was always like, we didn't have time for that, but now like reserve the 20 minutes for each physical or virtual meeting, but the whole meeting. So each half a year, and really see those points, because like the point about the updating the recommendation, it's hanging them for much longer than it should, because it was already done. So it shouldn't be on our short-term list. So kind of trying to update the website each half a year, and then having more actual decisions there. Okay, thank you, and sorry for extending it outside the meeting.
Maybe give back the floor then to Cel and Margaret to wrap up, I think, the entire meeting. Yeah.
Yes, if no one's got some quick inputs that are not really meant for sending by email, then we can close some meeting.
Yeah. Thank you.
Seeing none. No, thank you.
Thank you, Lucian, and the SAM group for a nice session. And I think we have had a very nice, interesting 4 days, a lot of interesting presentation, and we are now 8 minutes over time. So I just suggest we close the meeting unless Margaret want to add something now at the end. Thank you for hosting the meeting.
My pleasure. I have nothing to add. I'll stop recording, and I support closing here. Thank you, everyone.
Thank you very much.
Thank you, and
thank you,
see
Margaret.
you
Thank you,
soon.
Thank you all.
Next time. Bye-bye.